Welcome to today's Explainer. If you've ever stared at a medical study or a public health report and felt instantly overwhelmed by the absolute alphabet soup of statistics, well, you are in the exact right place. Today, we're going to tackle this together, kind of like a one-on-one study session. We are decoding the intimidating world of public health statistics into plain, understandable English. We're going to break down relative risk, the odds ratio, and attributable risk. And by the end of this, you won't just know how to read these numbers, you're going to know what they actually mean for real people.
Here's our roadmap for today. We'll start with the 2x2 decoder ring, move into understanding relative risk, break down the odds ratio, look at attributable risk, figure out which measure wins, and finally, wrap up by avoiding common traps. Let's get right into it. Section 1, the 2x2 decoder ring. This is literally the foundational matrix of all epidemiological measure.
Okay, so every single analysis, at its core, really just asks a basic cause and effect question. We're looking at two variables, the exposure and the outcome. The exposure is the factor we're studying. This could be a risk factor like smoking, or maybe a protective factor like a brand new vaccine. The outcome is the health event we're actually measuring, like developing lung cancer or preventing a viral infection. We are simply asking, does the exposure cause or prevent the outcome?
To answer that, we use the ultimate decoder ring, the standard 2x2 table. Almost all measures of association come straight from this simple grid. Notice how it's organized here. The exposure always sits on the rows, and the outcomes always sit on the columns. This setup gives us four very specific groups of people, neatly labeled mathematically as A, B, C, and D. Cell A, for example, is the group of people who were exposed and got the disease.
You really need to lock this mental image in right now. The 2x2 table reads left to right for the outcome and top to bottom for the exposure. The letters A, B, C, and D represent very specific groups of people. Don't ever change their positions, because absolutely everything else we do today builds upon this exact layout.
Moving on to Section 2, Understanding Relative Risk, where we compare the risk between two groups.
Let's build some intuition here before we touch the math. Imagine two different neighborhoods. In neighborhood A, where people are heavy smokers, 1 in 4 residents gets lung cancer. Now, in neighborhood B, where no one smokes, only 1 in 20 residents gets lung cancer. If I asked you how much more dangerous neighborhood A is, you'd naturally calculate that 1 in 4, compared to 1 in 20, is exactly 5 times more dangerous. That common sense ratio, comparing the risk in the exposed group to the unexposed group, is exactly what relative risk measures.
So, let's actually apply this to a hypothetical 20-year cohort study on smoking. Step 1, we find the risk in the exposed group. 200 smokers got cancer out of 1,000 total smokers, which is a 20% risk. Step 2, we look at the unexposed group. 40 non-smokers got cancer out of 1,000, giving us a 4% risk. For step 3, we just divide that 20% risk of smokers by the 4% risk of non-smokers. That gives us a relative risk of 5.0.
Now, here's the thing. A statistical result that just says R equals 5.0 means absolutely nothing to a patient or a policymaker. We have to translate it into plain English. Smokers are 5 times more likely to develop lung cancer compared to non-smokers. This right here is the real skill, turning cold math into meaningful public health communication.
Section 3, the odds ratio. This is where we work backwards from the outcome.
To really grasp the odds ratio, we've got to clarify what odds actually means, because trust me, it is not the same thing as probability or risk. If you have 10 smokers and 3 get cancer, the risk is 3 divided by the total 10. But the odds? The odds are 3 to 7. You're comparing the number of people who got the event to the number of people who did not get the event. Think of it exactly like betting odds.
We use the odds ratio mainly in case control studies. Why? Because in these studies, we the researchers deliberately select a certain number of sick people, the cases, and healthy people, the controls. Because we rig the totals, we can't calculate true risk. We literally have to work backwards. We use a really neat cross-product formula on our 2x2 table. We multiply cell A times cell D and divide it by cell B times cell C. If we plug in the numbers from a study looking at H. pylori and gastric cancer, that math gives us an odds ratio of 5.57. Meaning the odds of gastric cancer are about 5.6 times higher in infected people.
Okay, pay attention, because here is a massive exam trap, and honestly, a trap for anyone reading science news. The odds ratio only mimics relative risk when the disease is rare, meaning it happens in less than 10% of the population.
When a disease is rare, the odds ratio closely matches the relative risk. But if the disease is common, the odds ratio mathematically overestimates and completely exaggerates the reality. You cannot treat them as the exact same thing if the disease is common.
All right, section 4, attributable risk. Let's measure the absolute burden of disease.
This right here is why relative risk just isn't enough on its own. Take a look at a rare exposure compared to a common one. Mesothelioma and asbestos exposure has a huge relative risk. You're 100 times more likely to get it. But it's so rare, it only causes a tiny number of absolute extra cases in the whole population. Now consider the alternative. Hypertension only increases heart disease risk by a modest 1.67 times. But because high blood pressure is so incredibly common, it causes a massive number of extra cases. A modest risk for a common problem causes way more real-world harm.
That absolute burden is exactly what attributable risk measures. It gives us the absolute difference in risk between the exposed and unexposed groups. By simply subtracting the unexposed baseline risk from the exposed risk, we find the exact number of extra cases we could prevent if we completely eliminated the exposure. It literally answers the question, how many extra cases are caused by this thing?
This concept becomes incredibly powerful when we scale it up to the entire population. We call this the population attributable risk percent. Let's say we have a cohort study on obesity and type 2 diabetes. By applying this math to the entire population's data, we get 44.4%. That means eliminating obesity could theoretically prevent over 44% of all type 2 diabetes cases in our entire population study. That is a game changer for public health policy.
Section 5. Which measure wins? Let's figure out how to choose the right tool for the job.
This summary breakdown is going to be your absolute best friend. It clearly contrasts our three main measures. Notice how relative risk tells us how many times more likely an event is, and it's best for cohort studies or randomized controlled trials. The odds ratio is your go-to for case control studies. And attributable risk gives you the absolute difference, telling you exactly how many extra cases are occurring.
Let's use a really simple decision guide to lock this all in. Step 1. Got a case control study? You got to use the odds ratio. You have no choice. Step 2. If it's a cohort study where you followed people forward in time, use relative risk. Step 3. If you need to know the absolute policy impact to justify funding or an intervention, you need to calculate attributable risk. The absolute best practice? Always pair a relative measure with an absolute measure. That gives policymakers the complete honest picture.
Finally, Section 6. Avoiding common traps. These are the mistakes everyone makes, and exactly how you can avoid them.
First off, do not mix up your rows and columns on that 2x2 table. Exposure always goes on the rows. Second, please don't ever calculate relative risk from a case control study. It is completely mathematically invalid. Third, don't just assume the odds ratio is the same as relative risk if a disease is common. And finally, always remember that a relative risk or odds ratio of 1 means absolutely zero association between the exposure and the disease. The null value is 1, not 0.
So I'll leave you with this final question. The next time you see a scary health headline claiming a doubled risk, are you just going to accept it? Or will you ask if that's the relative risk and then demand to know the absolute attributable risk? Because remember, these numbers represent real people and real resources. Mastering these translations gives you the actual power to decode the truth behind any public health headline. Thanks so much for joining me on this explainer, and keep asking the right questions.